Well, good morning, everyone. It's a real pleasure to introduce my friend and colleague, Dr. Wei Fu. And he is a senior geomechanics engineer at Itasca, and he specializes in modeling coupled processes and subsurface systems. And so, as you can imagine, that work spans key applications in energy resource development, including hydraulic fracturing and unconventionals, THM modeling for enhanced geothermal systems, subsurface storage in deep geologic repositories, and hard rock preconditioning and mining. And before joining Itasca, Wei was a postdoc in the computational geosciences group at Lawrence Livermore National University. He received his PhD from the University of Pittsburgh, and in fact, his dissertation was recognized with the Dr. N.G.W. Cook Dissertation Award by ARMA. In 2024, Wei received the Distinguished Service Award and Best Paper Award from ARMA. So, a real pleasure today to introduce Dr. Wei Fu.
Thank you, John and Yeager, for the kind invitation. So really appreciate the opportunity to present and share some thoughts with the community. So the title of my talk today is Unraveling Hydraulic Fracture Complexity, Modeling Fracture Interactions, Swarming, and Near-Wellbore Tortuosity. Well, this is indeed a broad title, which touches on, I guess, a few areas that I know some of you in the seminar are still exploring. So I am definitely not aiming to cover everything or give definitive conclusions today. So the main goal today is really to share some work that I've been doing in the past few years and hopefully spark some good discussions or ideas along the way. So first of all, especially for people who are not that familiar with hydraulic fracturing, a brief introduction. So perhaps the most relevant area to the audience in this seminar today is unconventional reservoirs. So the production of unconventional oil and gas in the shale reservoir, where hydraulic fracturing is combined with the multi-stage horizontal drilling, which leads to the so-called shale revolution in the early 2000s. And the experience and techniques are being transferred to the geothermal area to develop enhanced geothermal systems. And a great example is the Utah Forge geothermal test site, where hydraulic fracturing in granite rock at about 200 degrees C is being tested. In addition to that, I also see a growing trend of using hydraulic fracturing in preconditioning in block caving. So this plot shows the hydraulic fracturing trial field tests in an underground block caving mine in Chile. So this method is being increasingly tested for preconditioning for the underground block caving mine in order to create tightly spaced fractures and promote the fragmentation during caving process. So with all these different applications in different geological settings, it is really important for us to understand the hydraulic fracture behaviors underground in order to optimize the stimulation designs for different purposes. So let me pull out my laser pointer here, okay. So here, I'm gonna use a simple sketch of hydraulic fracturing in multi-stage horizontal well as an example. So instead of homogeneous media, the subsurface can be inherently heterogeneous with various discontinuities, such as different joints, bedding planes, and sometimes big faults. And here's a plot of the natural fractures in the HFTS2, the hydraulic fracturing test site in the Maitland. So these are retrieved cores, which shows the sketches of the natural fractures on the interfaces. And these are calcite-filled natural fractures in the core samples jointing each other. So it can be natural fractures in the subsurface, and also instead of initiating one single fracture from each of the clusters, which has been widely assumed nowadays in the industry, some recent field tests also reveal that there are more complex fracture features, especially as shown in this plot. This is a 3-foot long core and we can see 8 of the fractures clustering within this single core. So it is growing in a swarming manner within a very short distance. And also in a region that is near to the wellbore, the behaviors can be more complex. This is mainly driven by the local stress concentrations and fracture interactions. If this is in a field of enhanced geothermal systems, you have another layer of uncertainty driven by the temperature change due to cooling or warming up of the fluid to the wellbore. So in this topic, I'm going to try to cover 3 of these different behaviors, hopefully give you some flavors for each of the behaviors. And then hopefully we can have some interesting discussions.
We can move 174.
Okay, so one of the main factors that may strongly influence the hydraulic fracture complexity is the existence of natural fractures. So here are some examples of the interaction behaviors. So the crossing behavior is shown in this plot, and then you can see in this plot, the fracture, the hydraulic fracture gets arrested by the natural fracture. Offsetting of the fracture behaviors features the fracture growing into the natural fracture, then initiate at the end of the natural fracture and continues to grow into the rock matrix. So in other words, instead of crossing the natural fracture directly, it generates a so-called offset. So unlike the symmetric and the planar growth, as one may imagine in a planar model or in a homogeneous setting, the hydraulic fracture can interact with natural fractures and leading to different behaviors. This sketch shows the fracture gets arrested by natural fractures, hydraulic fracture crossing natural fracture with some branching behaviors and also some natural fracture dilation due to shear slippage. Okay, so a lot of researchers have been focusing on this interaction behaviors and associated modeling. So here I'm listing a list of the analytical models that have been developed in the past few decades. So the early ones, the Blanton criterion, and then one of the most popular ones, Renshaw-Pollard criterion based on linear elastic fracture mechanics. And then later on, Gu and his co-authors further developed the behavior, the criterion into 2D criterion, but taking into account of the interaction angles as well as the summutation. In terms of numerical modeling, most of the widely used numerical simulators nowadays are either planar fracture models that don't consider fractures or pseudo 3D models that adopts, for example, 2D criterion and model the interaction behavior in a pseudo 3D manner. And there are also several models or numerical simulators that can do fully coupled 3D interactions between hydraulic fractures and natural fractures. So this plot shows an example of the unconventional fracture model in the kinetics. So this model incorporates the extended Renshaw-Pollard criterion for the hydraulic fracture, natural fracture interactions. In other words, it's also carrying a 2D assumption. So now the question becomes, how do the spatially varied natural fractures influence hydraulic fracture propagation, and whether it is necessary to include such features? So this is a good study by Gill and the co-authors. So they looked at the natural fracture properties in, I think, 18 different shale plays, and they have put together those summary, which shows the vertically shows the number of fractures and horizontally shows the fracture height. As you can see, the fracture really have different sizes. And the other 2 plots shows the summutation on the natural fracture interface. So this one shows the fracture surface with mineral coating, and this one shows the partially cemented natural fractures in a Marcellus shale. So the question is, how do we account for the heterogeneous natural fractures? Well, we may start with the so-called discrete fracture network, but it would be very complex to really isolate the interaction behaviors and look at how the spatially varied properties influence the hydraulic fracture propagation. So we do have a paper on the more complex interaction behaviors, but here we are gonna isolate the behaviors into a simple model. So this is a simplification of the interaction behaviors where we have hydraulic fracture propagating to orthogonally to a natural fracture. And on the natural fracture, it could be partially cemented as denoted by the hatched area here. And then it can be partially cemented or fully cemented. And it could also be that the natural fracture is frictional but shorter than the hydraulic fracture. And we look at its interaction behaviors. For this simplified analog model, we bring it into a simulator called XSite. It's a fully coupled hydraulic fracturing simulator based on lattice modeling. It's also a discrete element method. So as you can see here, we have a wellbore, then we generate a predefined crack to initiate the fracture propagation. And then the interface here is shown similar to the analog model here. And in the middle region with the green color, it's the cemented region, and top-bottom regions are the uncemented regions. So we will rely on this model to look at the interaction behaviors. And definitely before any simulation, it is always necessary to properly verify the numerical models. So here are just some examples of benchmark and verification of the XSite model. So the bottom two plots shows the comparison with the asymptotic solution for the toughness-dominated fracture propagation for the penny-shaped fractures. So you can see the crack opening and also the fracture net pressure compared to the analytical solutions. So overall, it has good agreement, although we do see some scattered distribution of the crack opening, but this is really because of the discrete nature of the discrete element modeling approach. And also, you can do further benchmark, but I will not mention too much details here. So let's look at the first simulation result. So the natural fracture with weak cementation. So some model settings listed here. In this plot, as you can see, the blue color shows the hydraulic fracture, and this green colored area shows the natural fracture. In this particular case, we have a weak cementation. And this plot here shows the fracture aperture along the interface or along the natural fracture. So as you can see, the hydraulic fracture is not able to cross the natural fracture, and instead it debounds the natural fracture and grows into it. So the bottom two plots, the left one shows the cross-section of the hydraulic fracture aperture along the horizontal plane. So the left side shows the location of the wellbore. The green colored line shows the location of the natural fracture. So as you can see, there's almost no fracture opening beyond the location of the natural fracture, indicating there's no fracture crossing. But if you look at the aperture here, you can see a large aperture distribution along the natural fracture interface. Again, these are just some further supports of the observation here that the hydraulic fracture is arrested by the weak natural fracture. The bottom two plots shows the net pressure distribution. It's relatively uniform because the case is in a toughness-dominated region. So another case, we look at the natural fracture with strong cementation. But here we changed two parameters. One is the fracture size. As you can see, for this natural fracture, we only cemented about 50% of the entire natural fracture. And the second factor is that we increased the cementation strength. So as we can see here, the hydraulic fracture is able to cross the natural fractures, even though it's about 50% cemented. In other words, the other half is totally uncemented. So as you can see on the aperture distribution for the natural fracture, there is a bright colored line indicating the higher aperture. This basically shows the location where the hydraulic fracture crosses the natural fracture. So further on, let's vary the cemented ratio of the natural fractures gradually, meaning from a fully cemented natural fracture, and gradually reduce the cemented ratio to 80% and to 40%. And as you can see from this interface aperture distribution, it also evolves from a fully crossed case to eventually the debounding without obvious crossing. So for example, this 40% cemented case, so the cemented region, although there are some highlighted colored region that could indicate limited crossing, but largely the interface is getting debounded. So the hydraulic fracture eventually is not able to really cross the natural fracture. So we also did a comparison with the 3D analytical criterion that we developed based on linear elastic fracture mechanics. So I will again not go into the details, but this criterion look at the natural fracture cemented ratio, natural fracture size, tensile strength, location of natural fractures, and host rock material strength, a few different factors that may influence the behaviors. We have conducted different scenarios. As you can see here, all the solid color is the case with crossing, and the hollow shape shows the fracture, shows the cases without crossing. So it actually fits the prediction of the 3D criterion really well. And you can find more information in the reference that I will provide afterwards. So a few key findings here to summarize. We find that hydraulic fractures can cross both partially cemented natural fractures as well as the frictional, relatively small natural fractures, meaning that there are quite a few scenarios that the hydraulic fracture is just crossing the natural fractures instead of being arrested or diverted. And also, under the simulation conditions, we find that hydraulic fracture can cross the natural fracture even if only 20 to 60% of the interface is cemented. And it requires a smaller cemented ratio as the cementation strength increases for the hydraulic fracture to cross the natural fracture. Another striking result that we find is that the hydraulic fracture can engulf uncemented frictional natural fractures with varying height depending on different simulation conditions. And strikingly, in one case, we found that even if the natural fracture is like 80% of the hydraulic fracture height, the hydraulic fracture was still able to cross the natural fracture. And this crossing ability increases in weaker rocks. So for all the simulations we conducted in this presentation, we were able to produce similar behaviors or capture the similar behaviors in a laboratory setting. So this one shows a case where we cemented the middle region. It's about 40% cemented, and top-bottom regions are uncemented. And as you can see, the hydraulic fracture was able to cross at the cemented region, and then it radiated to the top and bottom of the rock and continued growth. So this is a really interesting observation showing that the hydraulic fracture in many scenarios can cross the natural fracture. Okay, let's move on to the next topic, fracture swarming. So the swarming in the context of hydraulic fracturing is really used to describe a number of tightly spaced hydraulic fractures. And this is one of the earliest evidences of swarming hydraulic fractures from the Piceance Basin, Colorado, in the early 1990s. In this picture, it shows a sandstone sample where it has approximately, I think, 30 strands or 30 observed fractures identified over this 4-feet core. And it really challenged people's understanding at that time. But at that time, it was mostly attributed to the overpressure of the formation or the existence of the microcracks. And later on, from some recent field tests, we started to observe similar behaviors. This one is in the Maitland Basin, where we've already seen that 8 tightly spaced hydraulic fractures in a 3-feet long core. This is a hydraulic fracturing test site from the HFTS1, actually. And the bottom one shows another core sample with 7 hydraulic fractures. This is done by the ConocoPhillips at the Eagle Ford Formation. the big question here is how is the fracture swarm generated? Over the past few years, especially after the observation of at the Eagle Ford and Midland, there are a few conceptual models. Natural fracture interactions. Well, this one is likely to be ruled out because, for example, at the Eagle Ford Formation, according to the authors, they state that it's a region where the natural fractures are relatively sparse, or it's a quiet, so-called quiet fracture zone. So it's not likely that a natural fracture will have a big impact on the swarming behaviors. And also in the Midland, although there are a few sites of natural fractures, most of the natural fractures are cemented. So based on the first part of the presentation, we know that if the fracture is cemented and fully cemented, then in that case, the natural fracture also has limited impacts. So this factor, I think, is likely to be ruled out. And then we see other conceptual models, fracture turning and splitting at the fracture tip due to stress interference in different layers. And then in 2020, Alexei Savitsky did a research paper at ARMA, and he showed that the isolated tensile fractures can be created during stimulation due to varying stress and pore pressure gradient. One important thing to mention is that this is isolated tensile fracture, not directly connected to the main fracture. Whereas in the second bullet point here, it is actually connected. And then there are hypotheses. One of these is by Gill, driven by observation of the core samples. They stated that it could be partially due to segmentation and bifurcation of the hydraulic fracture propagation. And Joe Morris in 2022 showed that it could be also the Near-Wellbore effects that contribute to the hydraulic fracture swarming or more branches of the hydraulic fracture propagation. So this, as the sketch showed here, in a relatively simple way. And most recently, Liu and the co-authors, and I believe Yeager is one of the co-authors as well. So they show that the swarming can be generated during shut-in due to the delayed pore pressure drop in the rock compared to the fracture. So with all these different conceptual models, as we can identify the two cases where that involves power elasticity and pore pressure diffusion, the third one, the sixth items. So these two conceptual models basically assume the fractures are isolated, and the rest of the cases, the hydraulic fracture, the swarms, at least the swarms are connected to the main fracture. The rest of them are connected to the main fractures. So the question here is really more urgent, whether it is connected or isolated, because this will directly impact the stimulation modeling and as well as the reservoir modeling. Since if the fractures are not connected, although you have increased permeability zone, but the fractures are not propped and may have limited impact on the production. So with these conceptual models in mind, I would here personally argue that at least some of the hydraulic fractures in the swarms are connected to the main fractures. So here I will provide basically two parts of justifications. Although it's definitely not definitive, it's just for discussion or stimulating some new ideas here. So this one, we've already seen this photo. It's 8 tightly spaced hydraulic fractures. And as Elliott and Gill put in 2018, they found in situ sand patches in a few of the fracture faces, mostly in fractures near the proppant packs. The proppant packs, where the proppant packs exist, it most likely indicate a main fracture that accepts many proppants, and then near the main fractures, they find fractures with proppant patches. Although there's a debating observation that all the fractures, they actually observed hundreds of fractures in the retrieved core samples, and all the fractures contain at least some proppant, especially the very small ones. Whether these are due to core drilling or post-processing of the samples are still unknown. So that's a debating observation, just to put it here to be rigorous. And then we see in HFTS2, they did similar retrieved core. And this one, they observed 4 fractures swarm as shown in this plot. And the other 2 fractures, they think it's due to drilling. So in these 4 fractures, they found fine sand patches, which they interpreted as proppant. Although again, this is not definite, because those proppants, as you can, or these sand patches, as you can see here, they tend to have a smaller proppant size than the mesh that has been used in the hydraulic fracturing test site 2. Although they do argue that in any proppants, they will contain a lot of much finer sands in the proppants. That's why they still interpreted it as the proppant. So with these 2 observations, although, I mean, both of them are not strong evidence, but they are, I would say, some traces of evidence showing that at least some hydraulic fractures in the swarm are connected. They accepted proppants as part of the evidence. Although it's not strong, it's I would say it's sufficient to start with an assumption that some of the hydraulic fractures are connected. Based on that assumption, the next we want is to verify whether the assumption is correct. So the way to do it is to try to, like with this assumption, let's model the hydraulic fracture swarming in the field condition and see whether it could match the field observations. The first thing to do that is to develop an upscaling law in order to account for the tightly spaced fracture swarms. Because in those fractures, as you recall, there were like 8 fractures within 3 feet. These are sub-foot length spacing between the fractures, meaning it is almost impossible to model the fracture swarms explicitly in the field scale simulation. So here we started with field observations of swarms. So they are very tightly spaced, and most of them are parallel or subparallel. And then we aim to develop an upscaling approach carrying a few assumptions. First, each of the swarm consists a number of tightly spaced hydraulic fractures. And another implicit assumption here is that those hydraulic fractures are connected. And also the fractures are assumed to be parallel and identical. So the goal here is to represent a number of hydraulic fractures with a single fracture. So I will skip the details of the upscaling law derivation, but the main idea is to derive the upscaling law to represent a number of identical hydraulic fractures using an upscaled single fracture based on the energy equivalence argument. So to match the power of the swarming fractures with the power of the different upscaled, with the corresponding upscaled fracture. So you can look into this paper for the derivation details. This is based on PKN equation and for different components of the power associated with the hydraulic fracture propagation. So with the upscaling approach, we can achieve the upscaling law, where we will need to upscale the fluid viscosity, rock fracture toughness, and leak-off coefficient and proppant size, if you consider these 2 factors, in order to represent a group of hydraulic fractures with a single upscaled hydraulic fracture. So this is a summary of the upscaling law verification. So on this plot, you can see this is a group of 5 fractures. These 5 fractures are just illustrated in a way that the distance between the fractures are enlarged just for visualization. And this is the corresponding upscaled fracture. And as you can see with the upscaling, we were able to match the fracture aperture and as well as match the average length of the hydraulic fractures in the swarm and the upscaled fracture. So they match pretty well. So next, we want to take this into the field scale simulation for further validate validation purpose. So the cartoon here shows the different wells in the HFTS, hydraulic fracturing test site. The good thing with this site is they have really high quality macroseismic data. And as you can see, they also have 3D seismic data to define the layer boundaries as demonstrated in this plot. So here I select 4SM because this is one of the wells that has the highest quality macroseismic data. As shown here, this one shows the fracture extent, in the vertical direction and the horizontal direction in the macroseismic data. And this one shows the horizontal extension versus time. So as you can see, the vertical is the horizontal fracture propagation length, and horizontally is the time during pumping. So with this set of data, we can predict how the hydraulic fracture propagates or evolves at different time and compare it with the macroseismic data. So here we build a relatively simplified model as the first step to show how the upscaling approach applies to the field condition. So in this plot, I'm showing the simulation domain. We applied stress barrier to constrain the fracture head growth. And this fracture head growth is obtained by calculating the average fracture height from the macroseismic data. And then with average fracture height from the macroseismic data, we will be able to use the horizontal fracture propagation data as a comparison with the hydraulic fracture propagation. Here I'm showing two cases. One case shows a group of 5 hydraulic fractures in one stage. Each of the clusters is about 60-meter spacing. And this is without swarming effect. And on the right, I'm showing the 5 hydraulic fractures. Each of the fracture actually represents 8 of the fractures in the swarm, meaning with this single model, we will be able to simulate 5 hydraulic fractures, but each of the fracture actually have far more hydraulic fractures. In this case, it's 8 fractures. And this 8 number is obtained from the observations of the relatively dense swarming fractures in the core samples. So some of the modeling parameters that I will not go into details, but pay attention to the upscaling where the fluid viscosity and fracture toughness have been upscaled. So now let's compare the simulation results with the macroseismic data. So this one, the first one shows the conventional modeling approach, meaning there's no swarming. Each of the cluster has 1 hydraulic fracture propagating. So in a 5 cluster stage, you see 5 hydraulic fractures propagating. And we compare the propagation speed with the macroseismic data. And as you can see, actually, it overpredicts the hydraulic fracture propagation speed. At about 3,000 seconds, it already reached the boundary, but in the macroseismic data, this shows a much shorter fracture horizontal distance. By the way, this macroseismic data is obtained by stacking together 13 stages of macroseismic data so that we can get the averaged macroseismic distribution in terms of the horizontal distance. And now let's incorporate the upscaling law. In this case, each of the hydraulic fractures here represents 8 hydraulic fractures. And as you can see, we observe a much better fitting. So the hydraulic fracture propagation speed matches the prediction of the macroseismic distribution. That model is relatively simple because we didn't really consider the real 3D stress modeling or the real 3D stresses and varying properties in 3D. But that model gives us a good understanding of the horizontal fracture propagation and its comparison with the macroseismic data. And further on, we want to compare the fracture head growth for different stages. So here we constructed a more complicated 3D stress model following the approach of Coley and Zerbeck. You can look into this paper for details, but it uses 3 sources of data for constructing the 1D stress profile: ISIP data, DFID data, and log data. And then we make it conformal to the 3D geological layers to generate this 3D geomechanical model. So with that model, we are able to simulate the hydraulic fracture height growth in this simulator. By the way, this is the geo simulator. I forgot to mention, but this is when I was with Lawrence Livermore National Lab. So the geo simulator is based on finite element, finite volume approach. So as you can see here, I'm selecting two cases to demonstrate different fracture height growth. So at the stage 37, you see a relatively small fracture height growth, and at stage 25, there's more fracture height growth. And these 2 cases are the corresponding macroseismic events for the 2 stages, which show a relatively good match. And then let's take a look at the validation against the macroseismic data in terms of the height growth. So on this plot, vertical is the fracture height growth, horizontal is the time. So for 2 stages, as you can see, we achieved a really good match, both for the constrained fracture height growth case as well as the larger fracture height growth case. And it also captures the variation of the pumping rate during the hydraulic fracture propagation, and it matches the prediction of the macroseismic data really well. So a couple key findings here. We can represent the fracture swarming effect using an upscaled single fracture, and they attend good agreement with the field macroseismic data. And this upscaling approach is easy to be implemented into 3D simulation tools. And we want to especially note that to match the field observations, you will need to upscale the fracture toughness and viscosity. So in that sense, whatever conceptual models it will be in terms of the fracture swarming generation, I think it should somehow reproduce similar behaviors of apparently increased fracture toughness and viscosity, so that the hydraulic fracture horizontal growth, for example, will not be over-predicted. So this could be treated as another part of the support that some of the hydraulic fractures, at least, are connected to the main fractures during the hydraulic fracture propagation phase. Well, the last one is Near-Wellbore tortuosity that I will go relatively quickly. But in the first 2 examples, as you can recall, we tried to use relatively simplified approach to isolate the impacts of the particular factor and to understand the mechanisms. But here in the Near-Wellbore region, it is more challenging because it really spans multiple length scales, from the perforation scale to the nearby fracture scale. And also it involves different perforation tunnels that introduce local stress concentrations. And then there's the structure of casing, cement, perforation, rock interactions. And also there will be fracture interactions between hydraulic fractures and potentially natural fractures. In addition, there could be thermal impact in the case of enhanced geothermal systems. So it's really challenging to build something similar as what we have done for the first 2 scenarios. So in this approach here, we adopted a simulator X-site for the simulation of the Near-Wellbore tortuosity. But here, first, I'm showing you 2 photos of that could indicate some evidence of the Near-Wellbore tortuosity. Both of the 2 photos come from the Forge geothermal test. So the minimum instilled stress is about 6,000 psi. And as you can see here, in both of the cases, especially in the early time, the net pressure can be as high as 2,000 to 4,000 psi. Significant frictional loss or potentially Near-Wellbore tortuosity in the hydraulic fracture propagation in the Near-Wellbore region. So this is one of our motivations to look at this problem. And here, this is in a numerical setup. We are taking stage 4 in the camping of the forge stimulation for an example. So the model dimension is 6 by 6 by 6 meters. The stress condition is simulated the same as the real in situ stress, but here you're looking at the local coordinate, but after rotation, this is consistent with the field conditions with respect to the stress directions. So the wellbore is about 1.8 feet long for the perforated section. It has 6 shots per foot density perforation with a facing angle of 60 degrees and a total of 36 perforations. We modeled all the perforations explicitly, as well as the casing, the cement. And here are 2 plots showing the dimensions and facing angles and perforation tunnel sizes and lengths that we used for the simulation here. Some modeling properties that I will not go into details. You can find it in the paper. Also, we didn't consider leak-off. We didn't consider natural fracture in this case. And thermal advection in the fluid, heat transfer between rock and fluid are also not considered. So during the field test, we will have process of pumping down the tools using cold fluid. There will be pressure test before the actual hydraulic fracturing. So there are a few steps that will lead to the cooling down and warming up of the wellbore. So here we assume that the wellbore wall is fixed at about 100 degrees lower than the rock matrix, meaning the wellbore wall is 119 degrees C and the granite is 219 degrees C. And in the simulation, we also reproduced the field operations, meaning we do the excavation, we apply the casing and cementation, and then we do the perforation. And then we also do the wellbore cooling and for about 1 hour. And then lastly, we do the fracture propagation due to fluid injection. So one comparison here, just to show you, previously I showed the pressure plot during stage 4. And we can see there's the breakdown pressure of about 68 megapascal. And this is what we observed. This curve is what we observed in the simulation. So the early stage, we observe a breakdown pressure of about 71 megapascal. So it's close to the observations in the field condition. And here I'm showing you some behaviors of fracture, merging and longitudinal growth. So as you can see, this is the vertical cross section. So here we are looking at the fracture with an angle consistent with the field, but the maximum horizontal stress is perpendicular to the screen. As you can see, in the early time, the fracture merges into each other from different perforations. And also they grow predominantly along the wellbore in the longitudinal direction. It's actually in the plane of the maximum horizontal stress instead of the minimum horizontal stress as one may expect. So this is really due to the localized stress perturbations. And if we allow the fracture to grow further, as you can see here, there will be some curving start to emerging. So this is the plan view. Again, this is the side view. As the fracture propagates further, this part starts to curve, and it's easier to look at from the plan view. So this branch of the fracture starts to curve against the minimum in situ stress. So this merging behavior is captured by this simulation as well. And one thing I didn't include, but it's observed also in the simulation, is that the fracture started initiation both in the rock and also in the cement due to the combined impact of thermal cooling and also the in situ stress and near wellbore stress conditions. So that's an interesting observation. The hydraulic fracture could actually debound in the cement and initiates from the cement. So this is a comparison between the laboratory observations and our numerical simulations. This is the oblique well with 180-degree facing perforations. And in this particular case, you see the splitting and merging of different fracture fronts from different perforations. And there is also the debonding of the wellbore as described in this paper. And then there's a part of the hydraulic fracture that's turning into the far-field minimum in situ stress directions. As you can see here, this is our simulation. It's surprisingly matching the field, matching the laboratory conditions, although there are many different differences in these two cases. We have completely different stress conditions, and we consider thermal. Also, it's a much bigger scale. But again, you can see those fractures merging into the major fracture, and you can see the fracture turning into the far-field stress conditions, and there are some fracture front splitting observed as well, very similar to what has been observed in the field in the laboratory condition. So to summarize briefly, for the Near-Wellbore tortuosity, it really needs detailed well representation to capture complex Near-Wellbore behaviors. And also, from our simulation, we find that it still needs further optimization to reduce frictional loss and also improve perforation efficiency. It's not included here, but we do observe a relatively low perforation efficiency of about 20%. And it would be significantly valuable to have some monitoring, direct monitoring of the Near-Wellbore fractures, in which case we can further benchmark numerical models or improve our understandings, although it's really challenging. And for swarming, I would say it could be a combination of the fracture branching and segmentation during fracture propagation and tensile cracking induced due to poor pressure diffusion, either during fracture propagation or during shut-in. These two mechanisms in combination could contribute to the observed high density of hydraulic fracture swarms, because it has hundreds of fractures in the swarm, in the core, retrieved cores, and it should include both the fractures connected to the main fractures and also the vast majority of the fractures that are not connected. So that's just still an assumption or hypothesis. So another thing is the swarming really affects hydraulic fracturing and reservoir modeling. So either it's connected or disconnected, it will have a big impact on these two aspects. So we need further field monitoring and interpretation for this behavior. And lastly, for hydraulic fracture, natural fracture interactions, the primary take-home message is not all natural fractures matter, as we observe in the simulation and also in the laboratory experiments. Another thing is the spatially varied natural fracture properties and fracture geometries have first-order impact on the hydraulic fracture, natural fracture interactions. So to account for those behaviors, we would say it is necessary to incorporate large natural fractures, at least using fully coupled approaches, because those large natural fractures or faults will be able to divert hydraulic fractures and potentially change the trajectory. That's all for my presentation. So in case you're interested, here's a list of the papers that contain more details of the presentation. And I also want to thank my co-authors here, highlighted here. So thanks for the collaboration and all the useful discussions. And I want to thank Shell, US Department of Energy, GTI, and Utah Forge for the support and funding. Thank you very much, and I'm open to any questions.
Thank you, Wei. Three fantastic cases and some really great insights. We do have a few questions. We'll just see how many we can get through. The first question is from Noam Devori, and Noam is interested in how you represent the strength characteristics of the natural fractures. Did you use different fracture toughness values for the cemented fractures and the rock media?
That's right. In the simulation, using XSAT, for example, there are two ways to define the natural fracture strengths. In this particular case, we use tensile strengths to control the fracture strengths. And fracture, you can also use fracture toughness to control it. But because we developed a fracture crossing criteria based on linear elastic fracture mechanics, it's a strength-based criteria. So we wanted to be consistent in that sense. So we used tensile strengths and shear strengths to control the natural fracture properties.
And Wei, I'm wondering if you can go to slide 17 and Julia Gale, if you unmute yourself and just give us a little bit of context about this slide.
Yeah.
Well, that would be great.
Can you hear me?
Yes.
Yes.
I might have to run because my AC has gone out and the tech is on his way. But quickly, a couple of points. With the fracture, I think the overall point and great talk, very, very interesting talk, Wei. I really like it. So with the propant, we found propant in 2 or 3 places where there was complexity in fractures that weren't necessarily in a swarm. They were in an overall swarm, which was because the slant well in HFTS1 went past the stimulated well in the upper Wolfcamp, and that's where we found the propant. And I think it was to do with a mixture of things, proximity, maybe some, at the time we thought it was complexity in the fracture had blocked the propant from progressing further. One big thing that we saw was where we saw, you see in the picture there, where you got sand and no drilling mud, that's where we think the propant is in situ. If we observed, as you've got in that lower left-hand corner on this slide, all the fractures had some propant, but the point is they were entrained in drilling mud. And so we think that the drilling mud is just flushing propant in and out. So you don't know, for the vast majority of fractures, you do not know where that propant came from. There's a whole story on that, which I won't hijack this talk. So where we see the propant that's just a sand pack or a patch, we're pretty sure that it's in situ. So I think your overall point, to use it to the idea that it's connected to the hydraulic fracture is connected in some way, that's reasonable. The other point I wanted to make was we did actually do a spatial organization study. It hadn't been completely published. It was part of the reporting for HFTS1, so some of you will have access to that. And our point was that 8 tightly spaced hydraulic fractures, that's kind of an N member at that scale. You know, that was the highest number in a 3-foot interval. There's many intervals that have, say, doublets or triplets. And then there's that one that you've shown there that has 4 fractures in it. So the thing is that swarming in that 8, or in Ratterman's case, in the Eagle Ford with their 7, it does occur, and it's great that you're trying to model it, but it's not the norm, is what I'm trying to get across here. And the reasons for swarming, some of it I think you're tackling, and the other point is, in our observed data sets, is this variable that we couldn't control, which is the distance from the stimulated well, where the core is coming from, because it was a slant well and it went past the stimulated well in a certain section, and that's where we saw the uptick of the number of hydraulic fractures. So that's really what I wanted to say. If anybody has more questions, I can refer to them a little bit, and yeah.
Awesome. I mean,
I can answer that next question, Ed's question.
Sure.
So that image was something, that's a photograph that I did, or a figure I put together. That bottom part is the unwrapped CT scan. So it's showing a kind of shallow amplitude sinusoids of planar features. Behind it, if you look at the very top of that image on the left, you can see the actual core. Those fractures are pretty much planar. So it's the CT scan that makes those things look curved. They're not, they're planar. I mean, there's some that have curvature, and that's another story, complication. those are probably induced, but most of the hydraulic fractures are pretty planar. Some have steps and some complications, but yeah, that's the reason for that. It's the CT scan.
Thank you. That very helpful.
Thank you, Julia. That's that's really helpful, and I would encourage anyone who is interested in the core data or a more detailed quantitative analysis to look at Julia's paper. Quite a few papers, very good work. Thank you. It's really helpful to me.
Thanks. So, yeah, I appreciate it. And I think this is a really, really interesting talk.
Thanks.
Excellent. Excellent. We're out of time. Let's see. Luke is provided a paper that suggests an additional mechanism for branching and swarming. And I encourage people to look at the chat. Alexei has, as always, he's challenging us. Alexei, how about just taking 30 seconds and elaborate on what you've got there?
Can you hear me?
Yes.
Yeah, I think I had two technical challenging questions. Well, first of all, it's an excellent piece of work, and I especially liked fracture initiation, but everything is good. And my two technical challenges are, number one is how closely spaced fractures can propagate over long distances without changing orientation. So there is no stress shadow effect. It's very close spacing. That's still a mystery. So people who tried it would get deviations, and here it looks like it's all parallel. And second question was, you were matching to microseismic clouds. Well, first of all, on slide 24, it wasn't very clear whether the match was good, because calculated fracture height was within microseismic clouds, not matching the envelope. But second thing, it may be a moot point, because we saw in HFTS2 that microseismic dramatically underpredicted fracture height. So the most reliable data would be vertical, monitor well distributed strain sensing. And we saw in Permian that fractures are much, much taller than we thought. So I don't know whether you're trying to match it, but if fractures are much bigger than we think, both laterally and vertically, and laterally you can constrain it by crosswell monitoring with fiber or seal valve pressure monitoring. If fractures are much bigger, then the question is, can you make up mass balance? So if you start to split your injection rate between multiple subparallel fractures, would you still be able to produce big fractures propagating very fast?
Yes, thank you for the questions, Alexei. So for the first one, let me go back here. Yeah, I definitely agree with you. Like with most of the existing studies, because of stress shadowing impact, the hydraulic fractures won't be able to propagate to a very far distance. But here, this is a really simplified illustration, assuming that the fractures are all parallel and they're all growing in this fashion, like in an isolated way without merging. In the actual field, I would conceptually thinking that the fracture during propagation, it will have some segmentation, it will have some branching, and then after further propagation, they may again merge into one fracture, and then fewer fractures, and then further on due to either stress contrasts or local heterogeneity in the shale tightly. So it could again become bifurcated and branching. So the number here, for example, the n tightly spaced hydraulic fractures is really an approximation of these branched fractures. So as Julia commented here, like for example, this is an evidence of four hydraulic fractures with the sandpack as an evidence, but it doesn't necessarily indicate that this will persistent throughout the propagation. I think possibly it persisted for a few feet of distance, for example, and then it could merge or further bifurcate into more fractures. So again, the approach here is really to acknowledge that there could be bifurcation and branching that generate what we observed a part of the swarming in the core samples, not necessarily like they will persistent throughout the whole propagation. Yeah, for the second comment on the macroseismic data, I mean, this is really a good comment. I actually, if that's what you observe in the field, for example, then that basically means there's a difference between the hydraulic fracture propagation and also macroseismic locations. So here, what we do, as you can see, we actually assumed 8 hydraulic fractures in one swarm. And again, Julia commented that there could be, these are not the norm. Maybe norm is fewer hydraulic fractures, like 8, or not like 8, but 4, 3, or 2 hydraulic fractures. In those cases, the hydraulic fractures will be able to propagate much faster in this scenario. So again, this is not really a prediction. This is more of a so-called validation or comparison with the field data using the upscaling approach. And again, the number 8 is selected because we basically selected most tightly spaced fracture strengths and did a relatively general calculation of the number of fractures that lead to this number. But if you are assuming fewer fractures, which could be true, then the hydraulic fractures will propagate faster. And in that case, that may bring the simulation results more close to what you described.
I'm afraid we're out of time. And Luke and Santiago, I'm afraid you're penalized here, but just because we're out of time. But maybe if you can send your comments directly to Wei or your questions, I'm sure he'd be happy to address them or hear your insights. And if you don't have his email, I can provide that to you. Anyways, provocative and outstanding talk, Wei. Thank you so much.
Thank you, John, for the invitation again. Thanks.
And thanks everyone for attending.
You got to talk. Really great piece of work.
Thank you.
It's what's interesting is when you have the authors of the papers that you're citing on the same call.
That's right.
There's a little more pressure, but really nicely done, man. That was excellent.